Right, so this thing. So this is this paper about machine learning and artificial intelligence. What they're doing. So last time I went through spinal decomposition, which see I can pull that out too. That's what I wanted. I just want this, but I want to go here. Face stability. Let me get this guy. Did you look at the recorded class from last time?
Tuesday?
Yeah.
No, I didn't get a chance. I got back later last week.
Anyway, if you get into so this is this phase diagram, right? That's the free energy, and this is basically the Hildebrand equation with the two log terms and the I guess this is so this part you can forget about. That's this. So it's usually G minus that. So this is the ground base state, the base state free energy. So the first two terms you can just kind of ignore. It's really delta G anyway. And then this is the entropy part, and that's the enthalpy part. All right, this is just random marble mixing, and this is interactions, binary interactions. So if you get this, so there's a temperature for the entropy part. So as you change the temperature, the shape of the curve changes. So if you get to the immiscible region, so if you lower the temperature enough, then this repulsive term dominates and a phase separates. So the entropy always favors mixing, this favors demixing. So if you lower the temperature, this drops out, then you get demixing. In that case, this curve goes from being like a smiley face, concave up, to this kind of squiggle thing. So we have the frown face and concave down, that means you're getting separation. So because if you have a composition here and they fluctuate a little bit, the sum of the two fluctuations always goes down. So you're lowering the free energy by separating. So if you're in this region between the inflection points, the system automatically phase separates. That's the spinova region. It just spontaneously separates. So first derivative gives you the equilibrium phases, or phases are equilibrium, like the dark line, the binodal. And then the second derivative gives you the inflection point where it changes from a frown face to a smiley face. So the frown face is going to phase separate. Smiley face is not going to phase separate generally. So if you're in this, but the equilibrium points are here. So if you're in this region, you need a nucleus to phase separate. It has to grow on dust or something. If you're in this region, it spontaneously phase separates because in this frown thing wants to dump the phases. When it does that, it just decorates the so in the spinodal, it just decorates the fluctuations that already existed in the system. Like this, where that picture is, this picture. So it says there's a composition fluctuations. So it's just going to grow on top of those. Okay, so you might think, well, that looks like kind of could be a useful structure for some kind of application. I mean, I think this is what people thought when they first saw it. Although there hasn't really been an application where that's a useful structure, but nonetheless, that's something that people desire. So anyway, so that's what this paper is about, is making stuff with that structure. Like they want to make they're particularly talking about medical implants. So they want to make medical implants that have that structure so they can get tissue to grow into the structure. So basically that's what they want to do. And also the other thing they want to do is be able to, like when you have a real tissue, somewhere they show the gradient. So they want to be able to make a gradient of this this structure. So somewhere it shows like bone or something. Anyway, so they kind of show the gradient here. So they want to make an implant, like a dental implant, that's going to have that spinal structure out here, and then it gradually becomes a solid structure in the middle, so that they can that gives it the strength. So they call it the condyloid strength or something. It's like when bone meets bone, when tooth meets tooth. So that's where like you don't break the thing doesn't get loose. And the spinodal part is to enhance the biological interaction between the implant and the tissue around it. So anyway, so that's the goal that they have. So they're not actually going to make this thing. They're going to make the thing in a computer program. So they're going to simulate making that. So anyway, so how are they going to do that? Well, there's a couple ways to do it. One way is to take the spinodal has the Cahn-Hilliard equations that govern it. So this is a wiki page for Cahn-Hilliard, and this is like the equation that governs the spinodal. So it's like the composition develops in time. So that's a changing composition with time. And it's going to depend on the free energy, which in this case they're using, this is like a polynomial. So people who do computer programs sometimes just make up equations. So instead of using the Hildebrand equation, they're kind of just making up this polynomial equation. The advantage of this, so you can see, they want to have like composition because the spinodal is going to require the second derivative of free energy. So the inflection point to have a value, so they need to have an equation that's going to have a second derivative. So you choose a third derivative, third power, so they will have a value, a dependence in concentration for the second derivative. So this is like kind of an ad hoc free energy term. I mean, it's just something made up, right? So then this term has to do with the gradient that forms when this composition forms. So when you're doing a spinodal decomposition, you have a different kind of diffusion going on because it's spontaneously decomposing. So you diffuse up a concentration gradient. So like that, like this. So nucleation and growth, you have a nucleus, and that immediately when the material gets next to the nucleus, it forms the other phase. So it depletes the melt of the other material. So you have a downhill diffusion. You go from high concentration to low. That's Fick's law. Like the flux is going to be diffusion coefficient times the concentration gradient, right? And in the spinodal, it just spontaneously grows. So you're going up a concentration gradient. So the thermodynamics is driving the composition to just flux up out of nowhere. It doesn't have any depletion to drive diffusive motions. It just automatically grows, right? So in that kind of growth, there's a penalty to the interface like that. Like nature doesn't want to have this interface growth. Right here, you're going downhill. Here, you're going uphill. There's a penalty to having that interface. So basically, you have the free energy, which here it's an ad hoc function instead of the Hildebrand function. And then there's an interfacial term that's the penalty for having that weird interface. And there's some number here they call gamma, and most places they call kappa, which is the interfacial, it's like the interfacial component of this. So if you have that equation, which is called the Cahn-Hilliard equation, then you can put that into a computer program, and you can do what's called a phase field simulation, which it's not what he's doing. He's using that as a feeder to his artificial intelligence. So he's got kind of the same equation. This is the dc dt. This del has two terms in it. One is this interfacial, the first one, and the second is this polynomial. This, again, like an ad hoc replacement for the Hildebrand equation, right? And it's chosen because it's got a cubic term, and the second derivative will have a value, right? So in the case here, he isn't really interested in actually a physically real outcome. He's looking for something that looks like that. Like he's looking for something that's got the structural features of a spinodal so he can use that structure to do something with it. So he's not trying to understand thermodynamics here. He's trying to make a structure that he thinks is optimal for growth of biological tissue. So in that sense, it's okay to make up an equation for the free energy. In the case where you're actually trying to do something, probably not, but basically people do it anyways, especially computer simulation people. So he takes a finite element simulation, which is going to be like a grid with points, and then concentrations between the points. He's going to use this equation, the Cahn-Hilliard equation, to create like time sequence of events of the growth of this thing. So he's got pictures of that in here, of the growth of the spinodal, and he gets something that's pretty close to what it's like. Here's one example. So he begins the operation with a random. He's going to start with a random. So he's going to start with a grid of 64 by 64 voxels, which is like XYZ. So it's a volume element. It's a 3D simulation, so it's not pixels. Pixels is 2D, voxels is 3D. So he's got 64 by 64 by 64 voxels, and he's going to just pick a random number of kind of like yes, no, is it one phase or the other phase? And then he's going to use the Cahn-Hilliard equation to grow in time steps how that structure forms. And using that equation, it forms basically that high continuous network of constant mean curvature, and then with a fixed pore size distribution, I would say. So all these things are good for biological growth of tissue. So bicontinuous means that if I take an acid in and the red stuff dissolves in acid, then I can wash out the red stuff. In other words, the pores are all interconnected. And the red pores all form one solid object, and the bluish pores form another solid object. So there's no loose pieces left. That's what bicontinuous means. That's the signature of spinodal. Another signature is this constant mean curvature. And that's basically what happens when you have like a soap, when you put a wire into soap and you pull it up and you get a film that forms. So the curvature on that kind of film. So if you bend the wire into weird shapes, the film that you form has what's called a constant mean curvature surface. So the curvature as you go through the structure is always the same. So, and then because this is formed thermodynamically as a battle between the interfacial energy and the transport properties and the free energy of separation, you end up with a perfect spacing of these things. So they should have the monodisperse, fairly close to monodisperse phase size, and also close to monodisperse spacing of the phases, which gives rise to the if you shoot a beam of light through it, you'll get this scattering pattern, which has a ring. So you have your sample, shoot a beam through it, collect the pattern on a piece of paper. The main beam is in the middle, and then the angle of scattering is from there to there, and that's the size of your spinodal structure that's forming. 2 pi over that angle gives you the size of the phase. So you go up to large sizes, a small phase, small sizes, large phase. So if you look over time, that phase size, so this goes to a smaller angle. So basically you get a larger size. So as you grow the thing, you should see that the phases get larger. That you can see that in that phase field simulation, you get the growth of the phases to larger. Right. So this is actually his neural network simulation, but the phase field shows the same thing. This is, let's see. This is also neural network. He gives a phase field in the supplemental thing. Some places shows the phase field. It's the same thing. All right. Well, it's not in the supplemental. It's in here somewhere. Anyway, so that isn't what he's doing though. So that's this phase field thing. So that's kind of the starting point, and he's taken that as like the gospel. That's like the fact. So from that point, this is the way the world is. Now, he simulated it, but that's the way the world is. So he's going to say that's his target that he wants to get. The problem with phase field is that if you compare the time it takes to run a phase field simulation like that, so I think he has a plot at the bottom. No, in this supplemental at the bottom. So somewhere down here, oops, where's that plot? He compares the time that it takes to do the simulation somewhere. Not this. Right, it's going to be in here. Oh, here, right here. So this is like computational time to do the phase field full simulation is in hours. Right, so basically computational time means that the actual time that's going to take you is years. Because this is like the time that the computer is running on it, like a supercomputer, that it takes hours. That's basically a year's kind of thing, operation you're looking at. And then milliseconds is like a reasonable thing. So the millisecond thing is one time step in a simulation. He's doing I think 355 time steps, right? So the whole thing is going to take longer than the milliseconds. It's going to take seconds. Still a lot of time on a computer, basically. And the comparison is of the math model and then his CNN for all the different time steps that he does. So he's breaking up the growth of this thing, starting with a random and then going through various time steps, time jumps through, and it goes up to, I think he does like 300 time steps in the end. And each one is comparing. So then he has like this pair 1, pair 2, pair 3 of the time steps. Okay, so what he's doing is he's saying, if given this structure, and again, the phase field gave this to him, so Kahn-Hilliard gave him that sequence. If you have this random structure at the beginning, so he calls it random structure, the composition is this UAB. AB is the maximum and minimum of the value that it's going to have in this network. And it's random to begin with. So if I have that random one, and then I go to time 1, so what do I have to do to get that? So he calculates that with the phase field, but then he wants to just have, instead of a thinking operation, this is just a guessing operation. So he has all his pixels, and he's going to break it down. So we don't really need to understand. This is kind of like a black box in here for us. Basically, you take the pixels and you break it down to a simpler system, then you expand it into a larger system. And each transition of this has a weighting matrix that tells you. So initially you say it's going to be a random, it's kind of like a random process. So you have a weighting matrix for the 64 by 64 or 64 voxels to translate from one thing to another, and then another weighting matrix to another and another. Then finally, there's a deconvolution. So you're basically multiplying your numbers by another number to get a new number, right? But the matrix you're using to weight it is just a random bunch of numbers, a bunch of constants. So it's like whatever 64 to 64 by 64 is like a million constants, right? So basically you have a million constants to go from what you started with to get something else. And then you do that again, you undo that over here. So basically that matrix of conversion numbers is what you're operating with. So you say, if I have the beginning thing and then I have the end thing, so I have T0, T1, did I get T1 if I started with the same T0? So phase field took T0, you take T0, then you say phase field got T1, what did I get? And you compare the two, right? You compare the two, and initially it's going to be like a terrible match, like you didn't do very well, like 0.4. This is mean average error or something. This is the error between what he guessed it would be and what it is. What it is what the phase field simulation did. What he guessed it is what his neural network gave him, right? So it's terrible. So you go back and you say, like, I got to kick the matrix, see if I can make it better. You do that, and then eventually, as you keep kicking the conversion matrix, you find a conversion matrix to give you a perfect transition, right? So it goes to 0. You have 0 mean square error between what you did. So you haven't understood a single thing. All you've done is said, I have the beginning picture, I have it after one time step, I have this picture, and I have a conversion matrix, so I can generate that thing so that the two things are the same, right? And then I'm going to just keep doing that, changing my matrix. So you have a matrix then of numbers. It's a conversion matrix from the starting to the end. So you take the same matrix and you say T1, T2, right? And then, so you're going to tweak it until you get that thing to work right. So you just have a matrix of numbers where you can simulate spinal decomposition without knowing anything about what it is. It's just a blind thing. So you can do this with anything. Like you could do it with this, say, the stock market. Like all the history of the stock market, all the prices and all the stocks, and just say, that from 1 year later it's this value. So you can come up with a matrix that would give you that value. Then you say, well, can I use that same matrix to predict the stock prices next year or next week or tomorrow? Right. So this becomes like a pretty powerful thing if you want to make money. Like basically, you don't need to understand anything about the stock market. You don't even have to understand anything about money. You don't have to understand anything at all. All you have to do is have this matrix and you can predict the future. Right? It's kind of like magic. So this is what like a huge number of people are doing, this artificial intelligence, like predicting the future, Like if you take pictures of people, so you have billions of pictures of people, you take a random matrix of pixels with random numbers, say convert those to a picture of a person. And first time, like it's not a person, it's nothing, right? But the billionth time, it's a person that comes out of this. And then you can just start simulating people, pictures of people, or maybe even actual people. Right? I mean, it doesn't matter what you feed in, what you come out, it's just a matrix, right? So that's the idea of machine learning. That's basically the theme of this whole thing is you can imagine a lot of different mathematical ways to do that. There's a lot of nuances to it. Basically, that's what the machine learning idea is. Like it isn't artificial intelligence, doesn't have any idea what it's doing, but it comes out with the right answer. So he's saying that like if he does that, then he can beat the actual, so the guys that are smart are doing this, it takes them hours, and he's doing this, it takes him a second. Right. So it's like he's beating them, so he doesn't have any idea what he's doing, but he's beating them. Anyway, for his case, he doesn't actually need a real spinodal. He needs to make some kind of an implant that looks like a spinodal, that has the features of a spinodal, because the spinodal features give him narrow pore size distribution. So this is his CNN. This is phase field. So the actual Cahn-Hilliard, they kind of match up in terms of probability, and this is size, the phase size. And if you do it some other way, like just draw random blobs, you get a broader distribution that isn't as good because it's got these narrow passages in it. I mean, this is what he says. So the narrow passages, when cells want to grow into the tissue, that's a problem. Somehow it's going to be better if there's all the same size passages. He doesn't explain like why that is, like why it is better for a biological system to have all the same passage sizes, because biology isn't necessarily perfect, but he doesn't, anyway, he skips over the like why he's actually doing the thing. But this one is a little bit more convincing. Like he measures, so he can simulate flow through this spinodal structure. So he grows the spinodal structure, then he erases the red phase, and he just has that structure. So he can simulate flow through it, and he gets better flow with the spinodal. Let's see, where's the? Let's see. So this is interfacial area, and then it's effective diffusivity. So, I mean, there's a slight improvement. This is a phase field spinodal. This is his spinodal. So they're kind of similar. And this is random, just blobs that are thrown down, random blobs. Actually, the differences aren't huge, but basically he's claiming that that's a huge difference between green and green. And the blue is the interfacial. He wants to have the same interfacial area in between them to compare, and he's got better transport in the spinodal thing, even his fake spinodal. So that's kind of what he's doing here. All right, there's this other thing. So he's only simulating a 64 by 64 block of this stuff. And maybe these things are microns, or maybe they're millimeters. So he's beyond, like, so normal spinodal from metals, the size here is going to be like a nanometer. Right, the spinodal decomposition of metals, and polymers is going to be like 10 micron, because polymers are 1,000 times bigger than a metal, right? So basically, it scales with the size of the molecule it's separating. But he's making spinodal also that's macroscopic. Like you can see, I mean, you can actually see with your eye like the holes he's making, and they're in. So basically, it's like you can see them, so they aren't micron. Like a micron, 10, 50 microns of hair, you can hardly see it, right? So these are much larger than a polymer spinodal. So this isn't a spinodal that you could form with any real molecular system exactly. So what he's doing is he's making a CAD drawing of something that he could put into like a rapid prototype machine and then have it make this thing. Right. So, but you can't. So the normal, he's showing like the normal way you would do that is you'd make a grid of rods, or you'd make a grid of sheets. You make something, right? Some kind of repeatable object, so you can make like a repeating structure that you could make with it, right? So he's saying like this thing, right? So he's saying like if you made a tooth with a grid like that, it's got all these stress concentration spots. When you have this kind of random spinodal or stochastic, means random kind of structure he forms, it doesn't have stress concentration points basically associated with the mean curvature, like the bubble kind of shape, like when you take a soap bubble and make it on a randomly bent piece of wire, that's the minimum. There's minimum curvature, and it's also like the strongest structure that it could make of that shape, right? So the idea is like this should be the best structure, I guess. It's conjecture. Like he hasn't demonstrated that, so it's conjecture to say that, and it's kind of appealing, right? So you look at it and say like, yeah, that does look like biology. So that's basically the context of this whole paper is it looks good, so it must be good, right? He does do something kind of, so once you have all the voxels set up where the material is, then and you can make a large scale piece of this thing, then you can, in a computer simulation, you can do the flow measurement. So you can do that transport measurement through it. So you can measure the diffusion through it like this, like he's showing. But you can also take that structure and pull it and do like an Instron stress strain curve on it in 3D. Okay. So then when you do that, you get the 3D moduli of the thing. Okay. So like he says a C matrix. So this is something that you may or may not have heard of, so there's a pretty good little thing on this here. Which is worth reading for you guys, because this CIJ continuum mechanics thing, right? So this goes through like everything you need to know about continuum mechanics in like, I don't know how many, 10 pages, 30 pages. It's kind of a useful little document. I mean, so the problem with this, so this is easy. It's like stress. So this is the energy is the strain squared times the modulus at 1/2. So if you take the derivative of that, you get the stress and the strain and the modulus. Derivative of d energy, d distance gives you force. And so you get, anyway, derivative of that gives you this. So that's like if you have tensile, you're pulling on it and it's stretching in that direction. But this material is like complicated, right? It's not, so if you pull on it this way, it's going to change in weird ways in the other directions. So it isn't just Poisson's ratio coming in, depends on how squiggly the thing is. And it could even expand. Like it's possible to pull on something and have it expand, right? So basically you need to think about this as a tensor instead of as just a linear relationship, right? So you could, other simple, so this would be stress is a force going in the one direction, and then the area is the normal to it. So that's a tensile force, and the area defined by the normal to it. So it's a 1-1 stress. And then the strain is like you're pulling it, it's changing distance. The one distance is changing and it's going in the one direction. So it's a 1-1 strain. So it's 1-1 stress, 1-1 strain. But you could also have, if I pull it in the 1-1 direction, it could have a 1-2 strain. So it could have like a shear strain, could have a slip plane in it, right? So it could shear, or you could have a normal stress forming. So it could be a 2-2 strain showing up from a 1-1 pull. In other words, if it's got Young's modulus pulling in, it's got a 2-2 component to the strain of the thing, right? So it can get, so you have possibility of like 3 XYZ, 1, 2, 3, and then you have 2 numbers. So then you have 9, and then you have 81 total, because you have the strain has the same 2 numbers. So you have 81 possible moduli. These are going to be indexed with 4 numbers. IJKL. Right, so that's a C. That's a CIJKL. So it's stress IJ, strain KL. It might be too much for you to consume this right now, but I would suggest kind of looking at this a little bit so that you don't get shocked. So he's not using the 4-digit thing of this to make it even more complicated, because he says most of the time that matrix has symmetry to it, so you're throwing away, you get a lot of numbers you don't need. And then with different material symmetries, you can get rid of a lot of them too. So basically, and the only ones you'll ever use are going to be like the tensile, which is 1, 1, 1, 1, or it's going to be the shear, which would be 1, 2, 1, 2, right? So normally, except if you pull something like a polymer, like if you extrude a polymer through a die, it swells laterally. It's called a normal stress. And the harder you shear it, the bigger it swells. So that's called the normal stress coefficient. So that would be like one of these weird C numbers. I don't know which one, right? But so there are times when engineers use different combinations of these. But so the two, anyway, this is the 2 numbers. So there's a 4 number way to write the C, which is this is a modulus with 4 numbers. And then you can do this 2 number thing, which takes care of the symmetry thing. So that your tensile measurement is C11. And then, so the 2 that you're interested in are the tensile C11, and then the last one is C66, which is 1, 2, 1, 2. That's shear. That's when you shear something and you're looking at the stress, the strain, the shear strain. So you're pulling it in the Y direction, and you're looking at the gradient in the X direction, or the other way around. You're pulling it in the X direction, and you're getting the gradient in the Y direction. So it's like you move the deck of cards. It doesn't. So you're drawing something out, but the direction you're looking at the gradient is normal to the way it's changing. So the force is also, the normal to the thing is up, and the force you're putting on it is horizontal. That's the C66 in this context. All the other ones are weird, are oddball things that are happening, like when you extrude it, it swells laterally. It's like if you take a polymer and put it on the table and you shear it, you push your hand to squeeze it across, it lifts your hand up off the table. Put it that way. So it's like a weird, you don't expect it to push your hand up, but it does. Okay, so anyway. So anyway, that's the point of this. You need to know that to read this paper. So he's assuming, and again, this is in Nature, so it's assuming that a basic undergraduate education should make you that you know this. Nobody knows this unless you took a continuing mechanics class, and then you'd hate it so much that you would try to ignore it, right? Have you guys ever heard of the C11 IJK, whatever? All right, so anyway, this is the bread and butter. So read this thing. This is like the main thing you need to know. There's large books written on continuum mechanics. Everything you'll ever need to know is in here. You know, it's kind of a useful little ditty. But anyway, so he's saying this C matrix, and then he keeps talking about C has C11, 1, 2, da, 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 da. So only 6, 6, and 1, 1 are we really? That's tensile, that's shear, and the rest of them are oddball things that show up because this is an oddball structure. So it's going to do weird things. So he can put his spinodal things into a computer instron and stretch them and get the static strain of the thing from that. And he can do that both with the phase field model and with his stuff and with any other thing that he wants to put in. And then he can map out. So he's got every one of these. So because in a computer, you just push a button and it gives you the other one. You don't even have to understand what it is. So you can use that. So say he wants, so he's got one thing that he has is, it looks like the thing. It looks like the thing he wants. It looks like spinodal. And that's all he really wants anyway, but he wants to get it exact. So he does, well, we did this already, like a binary correlation function, which he calls a 2-point correlation function, right? So it's basically, you take a point here, I go out a distance r away. Am I in the yellow phase still? Yes is 1, no is 0. Then I'm going to do that for every point in the material. Then I'm going to do it in every possible direction. So it's a double sum of the first point and the second point. A double sum of all the possible first points and all the possible second points. And you're going to do that as a function of R. You change the R and do it again. And so you're going to have, is it correlated or not? When you're at 0, it's like 100% correlated because you're at the same point. It has to be, right? You divide that by the density, so it should be 1 at 0. And you see a depletion, nearest neighbor depletion, then you have a peak because this is a periodic structure. So in other words, it doesn't look periodic, but the distances between the phases are always about the same size, so you get a peak in this. That's a signature of spinodal, right? And then you go out, that oscillation for yes, no, as you go out, eventually dampens out because it averages out to the average density of the thing. So here's the average density. So he's going like percent pores, which is 1 minus the density, or 100 minus the density. So the densest one is the lowest pore. So that's the squares. So the squares have the squares have the highest density, right? So the highest, so this is reading that, so that's agrees here, it's good. High density, lower density, 45, 50% density, and the last one's 45% density, that's the lowest. They don't go, this should be like the distance between the first and the second should be the same as the second and the third, and it isn't. So I don't know why that is. That's kind of an odd thing. So if you have low density, if you have high density for the first one, then you'd expect to have the phases closer together. That's how it gets high density, because the hole between them is smaller. So that agrees, like as you decrease the density, the holes get, the struts get separated by a bigger distance. That's because the peak moves to the right in this distance axis. So that's good. And then the other thing that you can get from this straight up. So these are like, there's a lot of things you can get from it. You can integrate it, you can get a lot, which will give you the volume fraction. So you can get a lot from this in these curves if you want to analyze them, but just glancing at them, you can get certain features like the spacings, the distance from the peak, the densities out here. And the other thing you can get is that you go to smaller and smaller distance of this thing. And then you're measuring as if it's a flat surface. The correlation function has to do with the surface area. In other words, the amount of surface area versus the volume. So say you have two things separated by that, and they're in the solids. That's yes, till you get to the surface, and it's no, right? And then you get into the void, and it's no. So basically, the only no part is at the surface. So basically, that's going to give you the surface area for the correlation function divided by the volume, because you normalize them by the total. So anyway, the slope of this thing's a minus negative of the surface to volume ratio. So you expect if the sizes of the things are smaller, which they are in this case, because the peak's to the left, then you get a shallower, then you get a larger number for the surface to volume ratio. Right, smaller has a larger surface to volume. So and it's steeper, so that's good. So that one's okay. Then as you get to higher constant and larger phases, then you expect the slope to be shallower, and it is, but it isn't changing for the last two. It's the same surface to volume, whether you have 50% or 45%. Anyway, so there's something weird about the surface area of these things that isn't exactly right. So that's one of the questions. So that's one way he analyzes it. Then he analyzes it. All right, so this is an analysis, and he's doing what is it? He's starting. These are for different size. So he starts with one of his 64 by 64. Then he does a 128. Well, or he does a 96, and he does a 128 box, right? And he gets the same results. That's good. It means it's like it doesn't depend on how big his box is. So that's good. I mean, that's a nice little thing that he did. And then he uses the C thing. So he wants to, instead of trying to match, like here he's just matching directly the structure, right? And he gets, it isn't exactly the same structure. So he ends up with some of these little loose end things. So all right, he gets the loose end things. All right, so these boxes are repeating in space. Okay, so they're, let's see, shows that somewhere here. Shows that in here. So So when he makes it's gonna be a 60, but he can't make a whole implant with a 64 by 64 box. He has to make it with like a bunch of these hooked together. So the question is like, how do they hook together? Right? In other words, he's got the blue phase, it has to be continuous to the next box, right? Right. So he's got this repeating of so you see like this little divot here is the divot there, right? So it's a circular tiling of it. He's got, so this is the same box as that box, but I can line them up so that the blue thing just continues on, right? That's the only way that you could make this into like a large structure, because his simulation can't be the whole implant. You can only simulate that box, and even that's taken him a huge amount of computer time. Right, so he makes the box and he makes it in a way that he can get this this kind of repeating motif on the thing, right? Which is in let's see, circular padding, it's called. This is kind of some part of the thing, but basically, so one goes to like it's circular. It goes 5 1, then it would go 8 7 8, and then this way it goes 5 0. So it's 0 5 here. It goes that way and that way. So and it goes in 3D. Right. In other words, this is a problem when you're trying to simulate things. You can only simulate a little box and you want to have a whole building. But you're going to have some way to repeat it, to tile it, basically. There's different ways: replication, reflection, of this circular. So he's using circular. So that's one thing he's doing here. But so, and then I mean, one thing is that when he does this correlation function, so if this is really tiled like that, you'd get another peak in this thing. If this ran out to 64, he only goes to 30 because his box is 64. If he goes beyond that, he's going to see the tiles. The tiles will show up as a spike, like it's a crystal. I mean, it's like a protein can be a really complicated structure, but you can take it and put it onto an FCC lattice. You can crystallize a protein. So here he's crystallizing this in a simple cubic lattice. Right, so if you go out to 64, you'll see a diffraction spike, not just a broad peak, it will be a spike. So it'll be a huge spike over there. He didn't show that because that would be embarrassing, I guess. That means this material is not really a real material. It's got this repeating pattern, you know, that could, and he doesn't really say like what that repeating pattern could do to the properties when you try to grow bone in it. I mean, I imagine that has more impact than the whole spinol thing, but anyway, so that's one thing. So he says like, oh, I think what he did was he went and he tested his mechanical properties, and he said like, oh, they aren't good enough, you know. So then he said, well, instead of trying to match the structure of this thing with the spinodal, I can match the C matrix, so I get exactly the same mechanical properties. Right, so that's another way to do the simulation. So again, the method, the neural network is just like you're going to have a transform matrix. You're going to have something come in, transform matrix, and just multiply by a number, and you get the thing that comes out. And you kind of just keep tweaking those numbers until you get the thing to come out to look like the picture you want it to see. Oh, that's a person. Right here, that's a spinodal, right? Or whatever you want. That's a mechanical property. So you can put any property in at the beginning, any property you want at the out. And you can get any kind of transform matrix to get it to work. Right. So the thing doesn't know what it's doing, it's just trying to get the out to match what you want. So the out could be this C matrix. So he does that, and then he shows somewhere here. So he gets a perfect match eventually of these C11, C12. These are the errors. So the errors are really small. So you can get exactly the mechanical properties of the phase field, structure. He gets the mechanical properties by doing a Fourier transform of the mechanical response. So basically, normally Fourier transform is done at a time, like you do a Fourier transform of a IR. So normally it's a time transform. So basically a Fourier transform is going to take I mean, there's a lot in this paper that, you don't need to know this for the homework, but basically he mentions it. So it's important to kind of like see things. So you have something like a noise pattern, right? And then you want to say, and this is in time, or here, in his case, it's in space. Right, and this is the amplitude. So it could be the stock market price, could be like noise radio signal or something, right? So you want to do is take that. So Fourier theory says any signal can be broken down into like sine waves of different wavelengths. So you can say that thing would be like there's something like that in it of some amplitude. It's got a certain like wavelength or frequency. And then a wave number or wave vector Q or K. Like there's a lot of symbols used for the thing you're transforming. So you have the real space, this is called real space. This is called Fourier space. So you're gonna have like that thing, plus there's probably some noise thing like that. It's also a sine wave. So it also has a different amplitude, like amplitude 2, amplitude 1. And this is going to have like wavelength or basically wavelength or frequency to it. You can sum a bunch of sine waves to make so any signal you have, you can break down into a bunch of sine waves that have a wavelength and have an amplitude. I think you can plot that same thing as like amplitude versus say wavelength, and it's going to be like, oh, it's got spikes in it. And that could be a spectrum. So you could pulse it with a radio wave and watch how the signal comes out. So that'd be like an NMR or MRI measurement, right? You basically convert it to a frequency thing. And each of these has a certain like wavelength or nu or energy. So each one has an energy. So you can say like the energy distribution. So I go and shoot something with the radiation, or I hit it with a hammer and it's going to vibrate. So it gives off some noise. Then that noise you can break down to this and you say like, well, it's got this shape. Like one of the frequencies is the whole thing. So that the low frequency is like the big thing. There's a little frequency from that, that's that thing. So you can start picking apart what part of the thing gives the response that you see. So you can see like here he's got a mechanical complicated thing like that, and he's actually like pulling it, right? So it's going to have different size scale response to it. So he wants to break it into a frequency spectrum so you can kind of compare it on that way, you know. So that's why that's what he means by Fourier transform simulation. He's taking the structure that he made with the phase field simulation, the Cahn-Hilliard, and then he's whacking it in the computer, so he's just kind of vibrating it. And then he's looking at different size scales, deformations of the thing. And he's seeing how the response breaks down in terms of amplitude. So that's kind of what he's doing here. I'm not sure exactly how he's plotting this out, but basically he gets a perfect match when he compares his neural network thing and the phase field that he started with. That's kind of the point of this. So there's a lot to this paper. I mean, this paper is like pretty good, you know, I think to look at because it's got a lot of information in it, but just comparing the C things. What else? The Cahn-Hilliard's here. So the Cahn-Hilliard, so it doesn't exactly look like what we have from the notes or from these papers, you know. So it's because he's put in this ad hoc energy equation here. Like he's just stuffed that in. It's not, other people use the same equation, so it's not new. He didn't invent that, but basically, let's see, what else do I have here? It's a lot. I think it took me a while to read this thing, you know, so it's like, I think it's worth just sitting down and reading it, you know, and then try to figure out what's going on, and the things you don't know, like look up, and then it'll be worthwhile to look up the things as best you can, even without answering the questions. And then go back and try to answer the questions. You know? And like email me if you can't figure it out. So he wants to, what I didn't mention is that, so his starting point is this equation 1, I think, up here. More. So he says, this is a starting thing before he does any kind of manipulation. So the concentration is a random number between minus 0.7 and 0.7. And then below 0, it's the blue stuff, and above 0, it's the yellow stuff. And so that's his kind of original starting material. And then, so, but that's just going to give one block of it. What he really wants is this gradient. He wants to make an implant, he needs a gradient. So he has to have not just one kind of spinola structure, it's got to have like solid in the middle and get more porous as it goes out. So he introduces, and I don't exactly know how he does this, but he doesn't really explain things in detail in this paper, you know? But so, and he doesn't give any references to anything either. So it's kind of a little bit of a problem. But so if he wants the gradient, he adds in this cosine term. And R is a directional vector. So R dot X is like, would give you like a sine wave. Like in other words, as you go up in higher R, it's going to just be up and down, up and down. Right. So he adds in this weighting factor that shifts between, it's a 0.015 shift of his 0.7 range. So it's a slight change in his initial condition. And that's apparently enough to allow him to create gradients in this. Again, like the details of that are not in here. Like the details of how he does the Fourier transform aren't in here and aren't referenced anything. I mean, he gives you enough to kind of get a rough idea what he's doing, but he doesn't give you enough to actually check to see if it makes any sense. The few other parts, like he doesn't give any references. So a lot of this is because the whole neural network, artificial intelligence is like its own field. And the people in it, first off, they aren't scientists. They're just like computer geeks. And they don't really care anything about like references and things. And secondly, so they just want to get results. They're very results oriented, right? So anyway, and then the other thing is that I don't know what the other thing is, but basically that's part of it is that it's a whole, the other thing is it's its own field. So they've already defined like that he can just say CNN and everybody knows what it means to him, you know? So when he isn't really communicating it very well. Like there's a lot of things like that he just says. So you have to really Google like in artificial intelligence, what is a CNN? And you'll find out that document is going to be full of other acronyms. You don't know what they are. So you'd have to look up every one of those 30 acronyms to get a rough idea even of what's going on, right? So it's all acronym heavy. So it makes it a little bit inaccessible in that way. But on the other hand, it's kind of worthwhile because you're going to see you're going to see more and more and more of this. Because again, like business people love this because like they don't understand what's going on. This is a thing that's set up for people that don't understand what's going on and they need to know an answer like, should I buy GM stock or not? You know, it's basically no one knows. But you could make an artificial intelligence, it could tell you, yes, you should do that. It's like the Google search now comes up with the AI suggestions, you know, so anyway. So did you guys hear that Microsoft is going to like 3 Mile Island's a place where we had the biggest nuclear disaster in the history of the US. They almost nuked Harrisburg, and also downriver from that is basically Washington, DC. So very close to like nuking a big part of the US. So Microsoft bought the reactor and they want to start it up again just to do AI with it. This is not Bitcoin. No, but basically they're going to use a nuclear reactor is enough to power 300,000 houses. It's like basically 1 million people, you know, and it's like they just want to use it just to do the AI when you do the Google search or something. It's like pretty goofy what's going on right now. Anyway, so these people are a big part of that though. Like this kind of application in science is equally like energy consuming, but also kind of people are seeing it as, I mean, it'll definitely be something you're going to see. I'm put it this way, like tomorrow we're doing a tour in the other class of the Rumpke recycle. You guys can go if you want. It's at 1:30, but it's like 5 miles from here. But they use AI. So they have robots. So they like the garbage is going by, and the robot can pick out like a milk jug and all the things that are polyethylene. It knows the shapes of them from a camera, and a robot arm just goes in and pulls them out. So just learn this by like, no, that wasn't it. So it erases that idea. It's the same artificial. It's just got a matrix. So it's taking the input image, and the answer is like yes, no, milk jug or not. And it just modifies it until it gets it perfect. So it always gets milk jugs, always gets milk jugs, and anything else is kind of like polyethylene, high density polyethylene stuff. So it's everywhere. Like your car is going to do this. I mean, the cars already do it. Like the Teslas do it. Some of the GM cars have artificial intelligence. They're running the same kind of operation. It's just got a matrix, doesn't know what it's doing, but it's driving your car. So it's basically seems to be like the future, and it's appealing to kind of business people. Like your boss will love this because you don't need to pay someone to figure out what Cahn-Hilliard theory is. You just plug and play. You already got the matrix. It'll just make you as many Cahn-Hilliard theories as you want. It can actually make you a scientist, it'll do like anything. So it's pretty powerful as long as you have the nuclear reactor to run the AI. So anyway, so I think it's worth taking a careful look at this. I would, if I were you and I was starting out my career, I would learn every word in this, like every acronym, because those things are going to just get thrown at you all the time. And basically it's going to go over your head unless you pick up on it right now, like now's the time to kind of learn it and just get a feel for it. So, I mean, Cahn-Hilliard probably, you're not going to lose much sleep if you don't know what Cahn-Hilliard is. Basically the AI part of this is probably pretty valuable, I think. So, I mean, I'd encourage you to learn Cahn-Hilliard, but basically of the two, learning the acronyms in this and figuring out what a CNN means. Neural network, C is, I forget what C is, convolutional. So what it is there's three kinds of neural networks. I don't remember what convolutional is, but basically you should know that. I mean, that here, convolutional neural network. Let's see. I guess it's the original link of this thing. That's the PNG. Anyway, you can Google it. Wiki's pretty good at this stuff. The other thing about this stuff is that it's all already programmed for you. Like you think you have to be a computer person to run this stuff, but it's all just script lines and things. So I'll go over in the second to last section simulation stuff. You'll see I'll have you do a lamps like molecular dynamics, but they're all artificial intelligence is the same thing. It's all prepackaged software that someone else wrote. So there's like serious geeks somewhere that are like churning out this stuff. Then they make a package, and the more user-friendly it is, the more famous they get. So they make it user-friendly, and they have a whole team of other geeks that will help you if you need help with it. And it's basically plug and play. And it's free. Like it's not something like density functional theory. You have to pay $100,000 to walk in the door. This stuff, any idiot can go in, piece it together, and then get an answer out. Right? Kind of predict the thing, and then get a Nature paper. I mean, so it's kind of really useful for you guys I think it's really useful for you to kind of seriously look at this, even though it's challenging, right? And just try to weasel your way through it and get as much as you can out of it. And if it looks interesting to you, then pursue it. Like just do it. Like just figure out a problem that you're doing that you could apply this to, and just do it. Because that's the only way to learn it is to just pick it up as kind of like a hobby at first, and you'll find out that everybody wants to hire you to do it. This is the way, every kind of computer programming computer thing is going to be like, if you don't want to do it, don't do it. But if it looks like it's even marginally interesting, then just pile on as much as you can of it, because there's a lot of money in it. I mean, it's basically like people will beat a path to your door trying to get you to do things with it. Especially the managers of businesses who are the ones that count, because you can like do something no one else can do it faster, cheaper, without hiring anybody. So just the robot just does everything. Anyway, so yeah, that's the gradient thing. Fast Fourier transform, that weird equation is using. It's basically ad hoc, the equation for the free energy. Large structure. That's all I got here. So that's kind of, so when I go through the questions. So this is blah, 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 blah. There's a couple of links to things. So on the web page, there's links to that's good. That's like the simplified Cahn-Hilliard. The Hashimoto papers are pretty, like the best of them are not simplified versions. So what's circular padding, but this circular padding gives the answer in just one picture, right? And this you'd have to read the paper. And then I don't remember what this is also this idea of the CIJ continuum. This thing's good. And this is like a paper on it. This is a book on that same thing. So this thing's like 30 pages. I think this is a whole book. Like if you're really interested in continuum mechanics, and I don't recommend that you become interested in continuum mechanics, this is the thing that will kill your career. I think. But basically, I think this goes through everything you need to know about mechanical properties with respect to whatever. And then it's an old book, but basically it's a good book. I mean, Bourne is the guy, I think he won the Nobel Prize. So anyway, so what are the questions here? So yeah, so stuff definitely worth fishing around here if you can do less than the minimum on this. Wang calculates phase field, blah, blah, blah. Explain how these equations relate to Cahn-Hilliard theory. So there's that thing, and there's the wiki thing. And I want to start with the wiki thing because it's so simple. Like it's got two equations, the Cahn-Hilliard equation and a free energy equation. And you'll find, so use those as your touch points. And then you see he's got this empirical energy expression in this too. It's the same thing as in the paper. As far as I know, that might have been in the original Cahn-Hilliard, but basically the way people apply this is different than that. It's like this, right? So this is a real application of it, experimental, and it's got the free energy, it's got this interfacial term, but the free energy term is going to be the full Flory-Huggins equation, which he doesn't give in here, but basically that's a full like Hildebrand equation, the F here. And then he gives the derivative of it for the spinodal somewhere. Oh, here it is. So here he gives the Flory-Huggins equation with the surface term. So that's the Cahn-Hilliard for a real free energy expression, not this fake thing. And then anyway, this is a good paper. I like this paper, but basically you might not like it. You can look at it. And then so basically compare the two. I mean, there's some similarities. They're kind of similar, but basically there's some differences too. Like he isn't using a real free energy because it's the main thing. And then what's circular padding? I showed you what that was. It's like repeating the same structure over and over again, right? In all three dimensions. So you can make a large object out of a small voxel 64 cube thing. And then explain what circular padding, da, da, da. There's some links to help with that. So the signature is spinodal. So this paper is the only place where I've really seen this spelled out. I mean, I think it's just inferred in other papers, except that in this Hashimoto paper, constant mean curvature. I know this guy, so I just actually wrote a letter from him. He's winning a big prize. But basically, he's like the father of Japanese science or something or other. Like he's a good guy, but I mean he's old now, but basically, so he's talking about this constant mean curvature in here. He's showing pictures of it. He talks about it quite a bit, and then kind of figures out a way to analyze to show that it's got constant mean this is almost the same picture. This picture I've seen, it's been copied, I think, maybe even on this paper, right? But anyway, it's just talking about the constant mean curvature business. So that's one of the signatures. The other signature is you get periodicity, so the phases have to be repeat. So you're going to get a peak in the correlation function. It's bicontinuous, so the two phases are both continuous. So if you say you acid etch out the one phase, you end up with struts of the other phase, and it's a mechanically solid object. Like it doesn't have any loose ends floating around. Right. So all the phases are self-connected, and they're also interpenetrating, right? And constant mean curvature. So there's quite a few limitations on it. That's it, right? He lists in the paper. Those are the ones that he looked at. Interfacial concentration rate, smaller. Let's see. Let's look at a certain signature feature. The stochastic. Oh, I list some. So it's got to be a random structure too. It can't be like crystal with periodic domains. So if you shoot a beam of light through it, you get a peak, even though it's not a crystal. Interfacial concentration gradients go against Fick's law. So he doesn't really show that. A reverse diffusion interfacial, that's the same thing. And then 4B, page 6, demonstrates one of the features. 4B on page 6. Figure 4, figure 3, figure 4B. So that's this. So it's got the correlation peak, and that's it. It's just got the correlation peak. So it's got the phases are regularly spaced, even though it's not a crystal. It shows one initial, so it's one of these signatures. Initial slope, that's what I said, like it's the surface to volume ratio. So does that agree with that the density changes and the phase size changes? Those all have to be consistent, which I don't think they are exactly in this. For one, it's okay, but the other two might not be. Peak pertains to another feature of the system. These three features, correlation function for the three, agree with expectation. So yes and no. Consider that the learning sample is a square. So if he goes larger than that, he'd get a spike because it's a crystal. It's actually a simple cubic crystal repeating of that spindle structure. Right. So that would be disappointing if you looked at higher R for the thing. Figure 3A shows what appears to be Oswald ripening. So I talked last time about Oswald ripening. So basically, big fish eat the little fish. That's the rule of Oswald. So you're always going to have the larger phase just keeps growing at the expense of the smaller phases. That's the way it's kind of commonly referred to. It actually, when Oswald wrote about Oswald ripening, it was about crystal phases eating each other, like the lower energy phase being eaten, the higher energy phase being eaten by the lower energy. So it's kind of like, but the smaller phase is actually higher energy. So it's the same thing. Big eats little, but you can do high energy is eaten by this low energy is another way to look at it. That's the way Oswald looked at it originally, but anyway. Like when you nucleate and you have multiple polymorphs of a crystal, so the higher energy one is closer to the liquid energy, so it forms first. So when you nucleate, you get the high energy phases forming first, then the low energy phase, like the phase you want to grow, forms second, and it consumes the high energy phases. That's the way Oswald talked about it originally. But it's been taken to mean like small droplets have a higher energy than big droplets. So the big droplets eat the small droplets, and it reduces the overall free energy of the system. So you can see that in 3A is happening, even in this computer simulation that's going on. So 3A, so you can see the phases are getting bigger. Basically, and you're getting fewer phases, so the small ones are being consumed by the big ones. Big fish eats little fish. So that's Oswald ripening. You might want to Google it and get a real definition, but that's the way I see it. What is the final result? So if you go to Oswald ripening to the end, you're just going to get spherical domains. Because in the end, or you could just get the bottom and the top, like red and blue, right? So it could be just, so basically what people think about as the end is going to look just like nucleation and growth when Oswald ripening is done. It will just be, so you won't, so that this idea of spinola structure being different than nucleation and growth structure depends on the time that you look at it. If you wait long enough, they both look the same. Right, so it's all initial, and if you're doing metals, right, and it's happening so fast, you never can see it. It's gone before you can see it. But for polymers, it happens pretty slowly, like over minutes, hours. So it depends on the molecular weight. So then you can observe it. And you can also in that Hashimoto paper, you can see that the scattering collapses, and so that's Oswald ripening, like wherever he shows that the peak gets the smaller angle. So that's Oswald ripening going on. Then 3F and G demonstrates some of the expected behavior of spinola structures. So go through that. So F and G. So you expect to have a narrow distribution, the uniform, so fixed size with a narrow distribution. That's what that's showing. And then none of these narrow throats. You have the same pore size in the thing, which is associated with constant mean curvature. What else? Periodic structure, so it's periodic. I don't know, I don't remember the other things, but anyway, there's a few things in those pictures. Then finally compare the mechanical properties they are generated. This actually just like, what is the CIJ? What does that business mean? So it's kind of like regurgitate whatever's in that wiki thing. This business. Like kind of get to the point where you can talk about what is C11, what is C66, how they relate to mechanical properties. I mean, independent values for CIJ. It says theoretically is 81, but there's like half of those. So because it's symmetric matrix, I don't know, somehow you end up with, he has 6, I think, or something, right? So by symmetry things, you can reduce the number of them. Normally you're interested in only 2, C11, C66, which is the tensile and the shear. Anyway, that's about it. So it's kind of tough. You have to read the paper. It's going to take you an hour or two to read that paper, I think. Even just superficially. And then answering the question shouldn't be too bad. But it'd be good if you read the paper first. It's kind of a long paper. It's kind of like not that easy. It's good to have, because he refers to it's a typical kind of nature paper. He refers to the supplemental all the way through it, and the supplemental is pretty important to what he's saying, even though he's got a lot of figures in this. So, but basically, the supplemental is pretty useful to have when you're doing it. So it's good to do it on the computer and be able to flip back and forth. But try to look up as much as you can when you look at it, to try to figure out what this machine learning thing's about. That's about it. So, is that okay? Any questions or anything? No. All right, so right there, I guess.